All right. Take a seat on the stairs or find a seat down in front, and we'll begin. I first heard about the process of high harmonic generation at a Gordon conference probably about 40 years ago. And everybody was mystified by this of sending in laser light and getting out extreme ultraviolet and things like this by some nonlinear process that was not well understood. And then maybe about 25 years ago, I heard of the possibility of making isolated attosecond pulses by this process of high harmonic generation. And today we have one of the fundamental pioneers in this field, Anne LaHouillère, who discovered, in a sense, the process of high harmonic generation and the reasons behind it. That's the more important thing. Anne was born in Paris in 1958. She had her undergraduate education at the École Normale Supérieure and also got a double master's in theoretical physics and math from the same university. Then she went to the Pierre and Marie Curie University for a PhD, not in theoretical physics, but in experimental physics, and did a dissertation on multiple multiphoton physics ionization in strong laser fields. She had her first position at the CEA, which is Commissariat à l'Énergie Atomique. And there, she explored in great detail the process of high harmonic generation, recognizing that there was this unusual plateau of high harmonic peaks, which meant it wasn't an ordinary nonlinear process, but something very different, publishing numerous papers about the physics of this, working with theorists and other people to formulate a full quantum mechanical solution to it, to understand ultimately that it was like a recollision process in which an electron was driven off, tunneled out of the Coulomb potential and was driven back on and would recombine and produce this high harmonic radiation. And she also was seminal in understanding that in that plateau region of this long region of high harmonics, there was enough bandwidth to make isolated attosecond pulses. Then she obtained a faculty position at Lund University, and she had a postdoc in Gothenburg first, and also, by the way, in University of Southern California. So Anne has so many distinctions. I just want to mention three: the Wolf Prize, the BBVA Foundation Frontiers of Knowledge Award in Basic Sciences, and the Nobel Prize in Physics in 2023, which illuminated the fact that time belongs in physics, not just in chemistry. So I would like to just invite all of you to welcome Anne to our colloquium today and give her a big hand.
Thank you very much, Steve. Is it working? No. No. It's on. I need to move it. Is it better now? No. And now? Yes. Yeah. Yes. Okay, this is the outline of this talk. No, it's not working. I will first, I will give a little historical background to this field, talk about high-order harmonic generation, attosecond light pulses, and a little bit of applications in the study of electron dynamics. So let me start by the invention of the laser in 1960 by Theodor Meinmann, and actually Nobel Prize for laser physics went to Towns, who was here, right, in Berkeley. and Basov and Prokhorov. And they got a Nobel Prize in 1964 for their understanding of Maser laser principle. And what we use in our research is the fact that we can confine laser light in short pulses and that it's intense radiation. Invention of the laser opened new fields in physics. One of them is nonlinear optics, where new frequencies of light are generated. Here you have the experimental setup used by Peter Franken, and you have a laser focused into a piece of quartz. You analyze the radiation, you have a photon detector, and you generate, in this case, the second harmonic. Nobel Prize for nonlinear optics went to Niklas Blumbergen, and he got the Nobel Prize together with Art Shallow for their contribution to the development of laser spectroscopy. And in the same Nobel Prize, you have a Swedish physicist called Kai Siegbahn that got the Nobel Prize for high-resolution electron spectroscopy. Electron spectroscopy is really a fundamental tool in our field of research. Another field that was open because of the invention of the laser, very fundamental, atoms in strong laser fields or multiphoton processes. Here you have a two-photon excitation process. This was actually predicted theoretically in 1931 by Maria Goppert-Mayer. In the 60s, Russian scientists looked at multiphoton ionization. In 1979, Pierre Agostini and his group discovered above threshold ionization, where an atom absorbs more photon than what is needed for the ionization. And in the beginning of the 80s, my own thesis work was about the study of multiple ionization by multiphoton absorption. So at that time, it was kind of clear that in this interaction between atoms and strong laser light, excited species were produced, excited atoms, excited ions. And it would be interesting to look at the fluorescence emitted by these atoms. So this is the scheme of the experiment that we did in 1987. Very similar to the experiment by Peter Franken. We replace the gas, the piece of quartz with a gas of atoms. And we look whether we see fluorescence light. This is the laser that we used at the time, neodymium YAG laser, 1 micrometer wavelengths, 40 picosecond. It kind of looks a little bit old by today's standard. And this is the experiment. It's also an old photograph. The laser is here coming from the right. There is a lens here. And what you see is a vacuum chamber. You have two gratings, one here, one here. We were also looking in the perpendicular detection to look at fluorescent radiation. And you can notice that we use a printer to actually record the signal. The pen was linked to the photon detector. So this is really old times. What did we see? We did not see any fluorescent radiation. We saw a spectrum of high-order harmonics of light. Here you have a spectrum showing you harmonic 13 up to harmonic 31. If you plot the distribution of these harmonics as a function of order, you see the first decrease and then plateau, where all of these harmonics have approximately the same intensity, and then there is a cutoff. You can notice that we only see odd order harmonics. This is due to the symmetry of the interaction, killing even order harmonics. And maybe the biggest surprise in these results was this existence of this plateau. The reason is that at that time we were thinking very much in terms of perturbation theory, where you can expand the polarization in the medium in terms of power series of the electric field. And of course, here you expect the first order to be much larger than the third, much larger than the fifth, etc. And this was not the case. So non-perturbative behavior, very nonlinear and non-perturbative. To understand this process, you need to understand the atomic physics part of quantum mechanics, the response of a single atom to the interaction, which is described by the Schrödinger equation, as you see here, with the atomic potential and the laser atom interaction, described here in the dipole approximation. But you also need to consider the response of the whole medium in order to have a efficient generation of high-order harmonics. You need that all of the atoms in your medium emit waves which are in phase. So this is called phase matching. This is described by Maxwell's equation, which can be simplified to a wave equation as you see here. So you calculate the generated field due to the polarization in the medium. And actually the first attempts to describe this phenomena were by solving numerically these two equations, which good agreement, maybe this is good, but we would like to understand the physics behind the emission of this high order harmonics. Let me say that this term here is almost comparable in strength to the atomic potential, which makes this problem interesting and difficult maybe. Progress in laser technology in the 70s and 80s, leading to shorter and shorter laser pulse. And being here in Berkeley, also I would like to acknowledge the fantastic work by Cheng on this, using dye laser and making laser pulses shorter and shorter down to a few femtoseconds. 1990, you have the beginning of titanium sapphire laser, was discovered by Peter Moulton, and then new technique to generate femtosecond pulse. Also huge progress in how to amplify these short pulses with the discovery of the short pulse amplification by Donna Strickland and Gérard Mourou, leading to Nobel Prize in 2018 for this discovery. This is also the time where we build dedicated instrumentation to study high-order harmonic generation. This is an old photo of myself and my first two students in France. What we build is this instrument that you see here, which contain these elements, a gas jet, XUV optics, very important with good optics, to analyze the radiation, and then a photon detector, which in that case was an electron multiplier. Here you don't see the laser, it's behind the hole in this direction. Also, what happened in this time is this is when personal computers arrived in the laboratories, and we learned to do acquisition programs, and this was really a revolution how to take data in the laboratory. But you are too young to even know about that. This is how computers looked like at the time. So in France, we were using a laser where the short pulse amplification technique was implemented. So 1 picosecond pulse duration. It's based on neodymium glass, but really terrible pulse repetition rate of 0.1 hertz. So this was a very difficult laser to work with. So what do? Well, we travel. And this is a picture of the travel made by the spectrometer that you saw, plus myself and my two first students. We traveled to Lund for a few months using a fantastic titanium sapphire laser, brand new, implementing the different invention that I mentioned before. After that, we went 7 months working at the Lawrence Livermore National Laboratory, just very close from here, again using a very nice laser system. What happened afterwards? Actually, the spectrometer and myself, we went back to Sweden for a few months. Then I stayed in Sweden, and the spectrometer went back to France. This is the story of this setup. So I'm coming to the second part of this talk, attosecond light pulse. The idea came actually in the 90s and is presented on this cartoon. Let's consider 3 harmonics, the 3 waves you have on this slide. And let's assume that these 3 harmonics are synchronized. It's called phase-locked. We assume that all the maxima coincide at a certain time. This means that after half a laser period, the minima will coincide. Another half laser period, the maxima again. This is what is called phase locking. So we assume that we have this phase locking. If we sum these 3 harmonics, what do we get? We get a series, we call this a train of short light pulses in the attosecond range. Half a laser period for titanium sapphire is 1.3 femtosecond. So here we are in the attosecond range, sub-femtosecond range. And this represents the intensity of these pulses. If we have not only 3 harmonics, but let's say 10 harmonics, then we can get even sharper, pulses with even shorter pulse duration. So why does it work? First of all, we are in the extreme ultraviolet range. So high frequency, short light period. Second, we have this broad bandwidth given by these high order harmonics with the plateau behavior. So this is necessary in order to have short pulses. But the question was, are the harmonics phase locked? And actually it's going to take us, the community, 14 years between the discovery of high order harmonics plateau to the measurement of attosecond pulses. 1993 really breakthrough in the understanding of the single atom response. Why does an atom emit these high order harmonics? With in particular the 3-step model, which was proposed by Ken Kullander and Ken Schaefer, and also by Paul Korkum, and then formalized in a very nice quantum mechanical theory by Maciek Lewenstein. This cartoon explains this very intuitive picture. What you see here is an atomic potential which is deformed by the laser field in one direction at some time. And an electron here in the ground state can tunnel through this barrier. Then the electron goes away, few nanometers. When the laser changes of sign, the electron comes back, gets kinetic energy. At some point, there is probability for the electron to recombine, and in this process, you have emission of high energy photons. You need to understand that this is a very nice quantum mechanical phenomena. You can think in terms of wave packet, where part of the wave function is tunneling, driving away, coming back, and interfere back to the ground state. Now, I heard that there are many undergraduates in this room. Is it right? Yes? So let me give you a little analogy of this very nice phenomenon. So, and this analogy is called the adventure of an electron in the laser field. So you have an electron, a laser. The language is Swedish, just for... You can represent it like this. The electron is in a prison. It's good, otherwise we would not exist. It's a very strong force. But here on the side, what you see here is a roller coaster. Maybe you don't see it, but this is what it is. So, of course, the electron would like to have fun. So what does the electron do? Yes. The electron would like to escape. Yes. How? No? I hear some. You have to speak louder. And yes, it is tunneling. Yes, of course. Yes. Yes. Then the electron is very happy. This means acceleration in the laser field. I'm just helping with the language here. So it's going down and up. This story is finishing very bad. This is the end of the story. So the electron is meeting on its trajectory and the open prism and is falling. This is the recombination or recollision process and liberating its energy in the form of a scream, which is our attosecond pulse. Okay, this was finish this small parenthesis here. Okay, I'm just saying one more thing on this. What happens the next half laser cycle? The first half laser period, you have emission of an attosecond pulse. In the frequency domain, this is a broad spectrum with this actually plateau. The plateau can be related to the fact that the different electron trajectories here, where the electron is coming back with different kinetic energy, the probability for this electron trajectory is approximately the same. Now, after half laser period, you have the same thing on the other side. You get an attosecond pulse with the opposite sign. Your spectrum become modulated at frequency 2 omega. And this is repeated many times, and your spectrum the interference will be sharper. This is very similar to diffraction through multiple slits, where you have observed interference in the far field. In this case, our slits are in the time domain, and you observe your interference in the frequency domain, but it's the same mathematics. Let me say a few words about phase matching. In order to have phase matching, we would like the phase velocity of the fundamental to be equal to the phase velocity of the harmonics. So you want the refractive indices to be the same. So let's look at a very nice picture from the book of David Atwood. Let's see here. I like this picture very much. So here it's kind of general behavior of the refractive index of material. In the visible near infrared region, this is where we have our laser. The refractive index is larger than 1. And in the extreme ultraviolet, where we have our harmonics, it's less than 1. So looking at this picture, phase matching is not achieved. The refractive index are different. Fortunately, what we have is we have a little ionization in this process. Electrons do not come back. They just travel on this roller coaster forever. They get away. And so thanks to the presence of free electrons, we get an additional negative term here that lowers the refractive index at the fundamental frequency, and we can achieve phase matching. This happens for a degree of ionization, which is typically a few percent. It's not very much, so you cannot use a very, very high laser intensity, just a little bit, in order to have the single atom response, but not to win phase matching. In reality, I will mention that in a few minutes. It's a little bit more complicated. You have also influence of focusing and electron trajectory. I'll come back to that. So now we are in the end of the 90s, and we study these high harmonics in order to be able to answer the question, are they phase-locked? This is an experiment that we did in 1998 together with Mette Gordet. She was my first student in Sweden. She's from Denmark. Ted Hansch, Marco Bellini. This was a European collaboration. And we look at the coherence of high-order harmonics by making two sources of harmonic from the same laser and looking in the far field to the spatial distribution. This is a measurement that we get. You can see, I hope, very nice interference fringes, which show that this is a spatially coherent light. If we delay the two sources, and again, look at the spatial distribution, we get this distribution here where fringes have disappeared on the outer part while they are still present on the inner part. So this shows that we have really two contributions to the harmonic emission, and this comes from different electron trajectories, short electron trajectories leading to collimated emission, and long trajectories leading to this more divergent emission and reduced coherence time. So this results was really a confirmation of this three-step model with the different possible electron trajectories. It showed that harmonics were very nice coherent light, but it didn't answer the question of phase locking of the harmonics. So this was really solved by experiments by Pierre Agostini and co-workers, as well as Ferencváros that shared the Nobel Prize with me. Pierre Agostini measured attosecond pulses in a train of pulses, while Ferencváros could generate single attosecond pulse by using very short light pulse to begin with and measure them using a technique which is called streaking technique. You have an example of measurement in this case. Both used a cross-correlation technique based on laser-assisted photoionization of a gas. I'm going to explain in a moment in more detail the experiment by Pierre Agostini. So this was really the demonstration that, yes, this high-order harmonic generation leads to generation of attosecond pulses. Let me say a few words about the progress in the generation of attosecond pulses these days. So first of all, there again progress in laser technology with the optical parametric chirp pulse amplification, which is a nonlinear technique to produce short pulses and open for a new wavelength range in particular and short pulse duration. And nowadays, there is really a transition in laser technology with the ytterbium lasers providing very high average power and high repetition rates. Remember, we started with 0.1 hertz, and now we are doing high-order harmonic generation with 100 kilohertz repetition rate. So huge progress in technology. And these pulses can be compressed. There are new techniques to compress pulses. For example, in cavities, where you have a cell phase broadening in these cavities in a gas or in bulk material, and then you can recompress the pulse using, for example, chirp mirrors. Also, we have learned to control this strong field physics, to control this electron trajectory, to shape the spectrum. We can use different wavelengths, multiple wavelengths. There are many ways to control the emission. Here you have an example where we use two colors to generate not only odd order, but even order harmonics. And in this case, you have a rather broad spectrum while here we can actually have emission of just a few harmonics. Also, we have learned to produce harmonic with different polarization states and control orbital angular momentum. Let me also say a few words about how we control phase matching. And this is a little bit more advanced equation where we have not only neutral atom, but free electrons. This is what I discussed before, but also the influence of focusing and electron trajectory. And this is a plot of the conversion efficiency in argon for one harmonics as a function of pressure and length. And what you see on this result, this is simulation, is that you get a good conversion efficiency, about 10 to minus 5, not in a best point, but really on a hyperbole curve, which this shows that there are many different ways to achieve phase matching. You can choose to be here. This is the high pressure gas jet. Or here, this is a long cell with low pressure. You can even use semi-infinite gas cell. So there are many different ways to generate high-order harmonics, leading to similar conversion efficiencies. So this is a very flexible source. You can have long beam lines. You can have very compact, short setup. And again, very different ways to choose your gas medium. Now I'm coming to the third part of this talk, which is some application. And maybe I will be a little bit tougher here for the undergraduate students, but I will do my best, okay? So let's look at maybe the simplest process, which is photoionization of an atom. So this was explained, as you know, by Albert Einstein in 1905, and really was very important for the beginning of quantum mechanics. But Einstein really focused on the properties of light to explain the photoelectric effect and used the concept of photon, which was introduced before by Max Planck. Now here, I'm going to look at the photoelectron. Maybe you think of this photoelectron as a particle going to a detector, click, you measure its energy or its momentum, right? But we know that it's also a wave. And actually what we do with attosecond technique is to measure the wave properties of this photoelectron. So these are the questions I'm going to address. How long time does it take for an electron to be emitted? Can we measure the wave or quantum properties of the photoelectron? And let me start by how are these quantity measured. So we have our attosecond pulse train, or in the frequency domain, harmonic comb. And we ionize an atom. If we just use this light, we are not going to learn anything about the temporal aspect of the electrons. We just measure their energies. So our tool to look at the photoelectron is really this XUV light plus a probe field, a small fraction of the laser field, which is used to generate the harmonics. So in the time domain, this is an optical wave. Thanks to this probe field, we can have two photon transitions leading to sideband peaks, as you see here. So here you can absorb one harmonic plus a photon, or you can absorb the next harmonic, and then you have stimulated emission of one photon. So suddenly we have two quantum paths to access the same final state. We know this is quantum mechanics. We add the amplitude of this quantum path, and then you take the square. So what you get depends on the relative phase of the two quantum paths. We have a quantum interferometer. Now, if we want something to vary, in order to look at interferences, what we do is we vary the delay between this train of pulses and the optical field. And this technique has been called reconstruction of attosecond beating by interference of two-photon transition, or rabbit. This is the tradition of ultrafast optics to call this diagnostic method by animal names. So this is why it's called rabbit. How do we do that? In practice, we have a Mach-Zehnder interferometer that you see here. One arm, we generate harmonics or attosecond pulse train. We remove the fundamental field here with a metallic filter. And then in the other arm, we have our probe field. Very accurate delay variation. We are on the attosecond time scale for the precision of this interferometer. And so again, this is our tool. And we send this radiation into a chamber where we do photoionization, and we detect the electron. This is what is called a rabbit spectrogram. This is a measurement. What you see here is the electron spectrum as a function of delay, and what you see are nice oscillations. Let's look at the sidebands indicated here, and the information that we get is in the phase of this oscillation and how it varies from, for example, as a function of energy. If we plot what we do on a clock, 1 hour on this clock is half a later period, 1.3 femtosecond, and what we're able to measure is a position on this clock, not in absolute value actually, but we can measure very accurately how the arrow is varying. Again, for example, as function of energy or for different atoms. So what are we doing? We create an attosecond wave packet. We measure its amplitude as well as its phase using this interferometric technique. So this is the expression, the signal that we get. It's an interference signal. And again, the information is in this delay here. This delay depends on the group delay of the excitation pulse, as well as the group delay due to the ionization process. There is also a third term, which is a correction due to the laser field, which is used for the measurement, but I'm not going to discuss that. This correction is small at threshold and can be calculated. This is a kind of physical interpretation of what is this group delay due to the ionization process. It's actually a concept introduced by Eugen Wigner in 1955 as a derivative of the scattering phase, or half the derivative. It's half the derivative because we consider a photoionization process. It's half a scattering process. So it's the physical interpretation is the delay as the electron propagates in the potential. Let me show you an example, and this is photoionization of xenon in the 4D shell. What you see here is an old measurement showing a resonance. This is called a giant dipole resonance. It comes from collective response of the 4D electrons. So we would like to do dynamics. What is the dynamics of the 4D shell ionization? So here we have a time domain picture. This is what we want to have. This is a frequency domain result. We would like to go from the frequency to the time. In order to do that, we would like to do a Fourier transform. What is missing is the phase or the phase derivative, so the group delay. And this is really what we bring with our attosecond technique, is the measurement of this group delay. And here is a measurement. This is obtained for the 4D 3/2 electron using coincidence techniques. What is measured is really this delay, but we calibrate our measurement using the neon gas in order to calibrate this delay measurement and to remove the part of the excitation pulse. So this is what we get. You see that we have positive delays in this region, the region of the giant dipole resonance. See this peaked at 100 eV. So this, we see half of the curve here. That means that the electron is trapped a few tenths of attosecond in this case. And what you also see is that the curve is really increasing at threshold. You get long delays, and we interpret this as due to the spin-orbit interaction and spin-flip dynamics in this case. And the black curve are theoretical calculation performed using a random phase approximation with exchange and reproducing more or less these measurements. This is another example of these delay measurements. This is now argon in the 3S shell, and in this case you have a minimum of the cross-section. These are measurements performed using synchrotron radiation, and you have good agreement between different theoretical calculation and experiments. And this description of this minimum of the cross-section is called Cooper minimum, was really the success of a theory called the random phase approximation in the 70s by Amisha. So if you just do that, you are happy. Theory and experiment agree. So let's measure these time delays. And this is the measurements here performed by Chinese scientists. This is recent measurement. And what you see is the experiments show a negative delay here in this region, while the theory in blue, which is the result of this random phase approximation with exchange, taking into account coupling between 3S and 3P ionization channel, is showing this strong positive delay. And this is in this case, what we measure is the difference between delays in the 3S and 3P shell. But what you see here in this region, around 40 eV, is really due to the 3S ionization channel. So positive delay, negative delay in the experiment. Strong difference. Here we are almost 300 attosecond, and here minus 300 attosecond. So what happened is that we had new calculation performed by Evelyn Roth, adding correlation effect to this calculation. So we add new correlation effect, shake-up effect, and in this case, we could really reproduce the experimental results. So what this tells you is that thanks to our technique, we can measure this group delay, and we bring something more than just cross-section measurements. And we kind of push the theorists back to their computer or whatever they use and tell them, oh, you need to add something. We don't reproduce this, what happens here at the Cooper minimum. And they come up with, okay, yes, let's add this correlation effect, and now we can reproduce our results. Very different dynamics in these two cases. In the blue case, you have a strong trapping of the electron in this minimum, while in the red case, in the experimental case, in the real case, you have the opposite. The electron is pushed out of the potential very fast. Now let me finish by telling you about what we are trying to do now. What we realized is that sometimes we cannot consider this photoelectron as an optical wave with amplitude and phase. Sometimes you have addition of several incoherent processes. So what we cannot describe this photoelectron as a simple wave. We need to do something better. We need to characterize its quantum state. And this is a method that we proposed. David Busto here, Hugo Laurel, who's here, postdoc in Berkeley, where it's a variation of the rabbit method, where we use, instead of one probe field, now we use a bichromatic probe. So similar idea, we create a wave packet, in this case using a single harmonic. This is the blue cloud that you see here. And we address this wave packet by using this bichromatic probe. So we create a sideband and we measure the electron energy. So what is the idea here? Let me split the XUV photon into two, just to explain the idea. And what you see is that, again, you have two quantum paths going to the same final state, this epsilon f here. And you are going to get interferences when we evaluate the delay. But now the contrast of the interference pattern is going to depend on whether there is a well-defined phase relationship between these two energy states, epsilon 1, epsilon 2. In other words, what we can measure is the coherences of the electron wave packet. So if we do that, this is the interference signal is going to vary like this, with here not 2 omega as before, but delta omega, omega 1 minus omega 2. And the contrast of the oscillation is going to be proportional to the density matrix, to the coherence, while the phase is going to be the phase of the density matrix elements. This technique, it's a tomography measurement of the electron wave packet. The name is, we call this technique by Kraken. This is, I think, a rather bad acronym. You need a little bit of Swedish in order to get the K. I think Hugo here is behind the invention of this acronym. So anyway, so this is measurements performed for different delta omega, and from each measurement, you can extract the coherences of the density matrix. This is a measurement performed in helium. So the density matrix, you have energy in this axis, energy in the other axis. This is the diagonal of the density matrix in this direction. So from each measurement, we can determine a subdiagonal of this density matrix. From this now measurement, we do a little bit of AI. We use a Bayesian optimization procedure to recover the density matrix. This is what you get. It's rather nice density matrix. Its purity, it's very close to 1. So in this case, we photoionize helium in a region where you don't have any resonance or anything, and we get a coherent state and with density, with a purity equal to almost 1. Let's do the same in argon. And in this case, what you see is an oval density matrix. So this shows that we lose coherences a little bit. So we have a mixed state. And we can measure the purity, and it's equal to 0.65. What happens in argon? Spin-orbit interaction. When we photoionize argon, we actually have an entangled state, an entangled ion electron state. The ion can be left into two different states, 1/2 state or 3p states, as you see here. And we are not measuring the ion, so that we measure a reduced density matrix with a purity less than 1. If the two distributions that you see here were not overlapping at all, this will be maximal entanglement, because if you measure an electron with a certain energy, then you know the ion has a certain angular momentum. In that case, the purity would be equal to 0.55. In our case, there is a little overlap here. So when the electron is emitted with this energy here, you don't know what is the angular momentum of the ion. So I'm now concluding this talk. I think attosecond science is extremely open at the moment. It goes into many directions. I presented some application in atomic spectroscopy and a little bit opening towards ultra-fast quantum dynamics. I think one challenge of our field is to show that it can be applied to more complex systems, to molecules or condensed matter. And I have seen a very, very nice experiment in today at Berkeley on this aspect, in particular in the group of Steve Leone. There are also new sources of attosecond pulses. I have described attosecond sources via high-order harmonic generation in the XUV, rather low energy per pulse. Now there are really very nice results using free electron lasers, in particular the LCLS, just very close to here, with attosecond pulses in the X-ray range and much higher energy per pulse in the microjoule range. So there are a lot of very nice physics which is done using these pulses. So with that, I would like to say that this work has really been teamwork and collaborative work. This is a photo of the group in Lund doing this physics. This is the list of the senior researchers working with me on this subject, and Marcus and Eva theorists. These are organizations financing this research. To finish, I would like to really thank you for your attention. I would like to thank University of Berkeley for your invitation. Just to finish by a little bit of a joke. When you get the Nobel Prize in Berkeley, you get a parking place, right? This is what I found on the internet. I tried to look for it yesterday, but did not actually find them. But so what do you get when you get the Nobel Prize and you are in Sweden at Lund University? What do you think? 2 parking lots? No. You get a bicycle parking lot. So thank you. You're welcome to visit Lund, and you will see this. This is
I'm sure Anne will be happy to answer some questions. Raise your hand. Over here.
yes.
When you were talking about principal harmonic generation, you showed a waveform of this attosecond pulses separated with femtoseconds.
Yeah.
How did you measure the waveform?
Well, the waveform we did not measure.
Oh, so what was shown on the plot then?
The plot was just summing the high-order harmonics.
Oh, it's also mathematical.
It's mathematical, yes.
Okay.
To my knowledge, the waveform has not been measured. Just the pulse duration.
I see. Now I understand.
Yeah.
Oh yeah, up here.
So the question is, what are the challenging questions? Yeah. What is still the most challenging answer, or what was? Yeah, I think I said it. I think the most challenging question was: are the harmonics phase locked? maybe it seemed natural for you that they should be. First of all, they are not exactly. There is a chirp, so the trajectory do not come back exactly at the same time. And actually at the beginning, and because of these different electron trajectories, this short and long, if you add this contribution, you get interference effects. And the theories were showing that, oh, but you don't get this phase locking. It was not a trivial, it was not as easy as it seemed. So for me, this was the most challenging. The other challenging was how to detect this, to measure the attosecond pulse. It was not clear. It took 14 years to find the method, and it was solved by Pierre Agostini and Fair and Cross to use this cross-correlation technique. So this was also very challenging. Remaining challenging questions, I mean, we still battle with rather low efficiency. So we would like to improve this efficiency. We would like to improve the flux of these sources. Yeah. And also to extend it to higher photon energy. Remaining challenges is also to apply these pulses to interesting physics or chemistry.
Yeah, here.
So it's a little bit general, and you talked about it a bit at the end, but what is something that you currently don't know but want to try and understand?
I come back to this slide. I think I am very excited by this connection to quantum information. I think it's really interesting, and we are trying to develop this Kraken technique to use it for more complex system, and we are also we are going to try to use different non-classical fields to see how it affects what we can observe. So I'm very excited by that. No idea where it goes, but it's very interesting. Again, a challenge, I think, is really to use these techniques to follow electron dynamics in more complex systems and to really understand what is happening. Yes.
Yeah.
Thanks, Paul. Is there a theoretical upper limit on how short you can make your pulses through
There is no fundamental limit, I would like to call it this way. And you can generate a really very, very broad plateau nowadays if you use mid-infrared radiation. Difficulty is to actually have all of this broad plateau, to have a phase locking over a very, very broad spectral range. So that's a limitation to how short we can get. The record, I heard that last week actually, is 19 attoseconds. This is a record of pulse duration these days.
Back.
What sort of dynamics would become accessible to study at that shortest, or like if the duration is pushed down even further?
Yeah, I think what I showed is really looking at electron dynamics in outer shell or just the shell just below the outer shell. If we have higher energy photons, we can look at core electrons. So different dynamics, maybe even faster dynamics. And then we can get site selectivity, which is also important.
Okay. Yeah.
You said the record was 19. It was at Attosecond right now?
Yeah.
How many harmonics is that?
How many harmonics? I can't do the calculation by heart. But it's you need to I think they use like mid-infrared radiation or 2 microns, so you need to be in the few hundred electron volt central photon energy, and then have I would say 50 eV or something like that. This is really like this. I can't calculate like this now, but rather broad.
Let's thank Anne for a gorgeous talk.